Hello everyone, my name is Kuoyue from Biomedical Engineering Department. My project is precision electrode placement using brain imaging. My supervisor are Hamish and Christine. So first of all, I will introduce the background of project. Electrode array positioning is a difficult stage for both clinical and research fields. Electrode implant, deep brain stimulations, and therapy for Parkinson's disease require precisely electrode placement. So in terms of clinical needs, this technology reduces potential risks when electrode implant. Meanwhile, it will explore more therapies for clinical treatment. For research needs, electrode positioning is a basic neuroscience tool. Scientists can understand function and structure of the brain. So the project aims to develop a system that combines brain imaging with adjustment using a macro manipulator to position microstructure electrode array in precise cortical layers and within precise orientations. So this method concentrates on the orientation of electrode corresponding to the direction parallel and perpendicular to the cerebrum cortex. So the design process contains two stages. So one is image reconstruction, that is construct a three-dimensional structure from original images. The second one is positioning penetrating electrode array by a macro manipulators. So at stage one, brain imaging is a non-invasive technology to capture structure of the brain. Image captures use OCT or microscope record a series of image data from 1 to 90 depths. After the image capture, imaging analysis and imaging improvements are required applied for the model development. Image analysis use fast Fourier transform and power spectrum analysis. Imaging improvements redefine abnormal regions through averaging outline pixels. So I use the fast Fourier transform for imaging signal process. Fast Fourier transform theory understands image characteristics. Importantly, it reviews details of brain surface and structures. Extract signals from brain imaging can construct three-dimensional structure of the brain. So Fourier transform is a powerful tool for signal analysis. It converts signal from time domain into the frequency domain, which is easily to visualize the high frequency range. So fast Fourier transform assume it is a stable, periodical, and continuous signals. However, actually signals are finite length and non-periodical. And so I segment several time intervals which contain stable and periodical signals. For reduced spectrum leakage, I use the Henning window function during the signal segmentations. So in my case, the golf ball images is an example. In the frequency domain, there's a peak in the power spectrum with high power density at pixel. Preliminary depth map is acquired from initial power spectrum analysis. However, the map doesn't show what we expected results, which doesn't show a Bose fair because there are artifacts, especially for ages. So noise may come from the image capture and Fourier transform. So the image improvement is necessary. Firstly, image mask detect particular regions where are abnormal regions. Then outline of the regions take average values. Averaging at pixels redefine abnormal regions. Finally, I got the improved map and develop three-dimensional structures. Stage two is the positioning penetrating electrode array by macro manipulators. So there are two primary aspects to be determined for positioning penetrating electrode arrays. So first one is the position on the surface and the depth relative to the anatomy or functional organization of the cortex. The second one is orientation of electrode to the cortical surface. So finally, I got depth map and reconstruct for the structure of the ball. That simulates brain surface. Then I would do the experiments on the brain in the lab. This project utilized OCT for creating three-dimensional image of the cortical surface. Then the micromanipulator inserts implantable arrays into the cortical surfaces. Okay, thank you. Join my presentations.